deformation processes. I'm now going to continue talk from what we talked about yesterday, the brittle deformation, and talk to you about ductile deformation, as well as introduce some of the different styles of deformation we see under different plate boundaries and tectonic situations. So just as a reminder, when I talk about stress, I'm talking about force per unit area. As you'll know, there's a lot of tectonic force being experienced by a lot of the crust at any one time. And there are three main types of tectonic force. We talk about tensional forces, where rocks are being pulled apart. Compressional forces, where they're being squeezed together. And shearing forces, where one part of the crust is being moved in a different direction to the other part of the crust. And that diagram I showed yesterday illustrates that nicely. And when I talk about deformation or strain, this is the response of a rock or earth material to that stress, and it usually involves a change in shape or size of that rock. So I talked about three types of deformation, so three types of strain. There's elastic strain. This is where when the stress is applied to the rock material, it changes shape or size, but when that stress is removed, it returns to its original form. So as I said yesterday, we're not interested in that in geology, we're interested in looking at evidence for processes in the past, and if there's been elastic strain, obviously we don't see any evidence in the rock record. I talk about ductile deformation, which is the next phase. This is where you have a change in shape or size of the material, but it's permanent, you don't go back. But we haven't actually broken the rock yet, we haven't fractured it. We've gradually bent it or changed the form of it without breaking that material. And yesterday I introduced a little bit about the different styles of brittle deformation. So brittle deformation is where you've stressed your material so much that it breaks, it fractures. And obviously that is also permanent and irreversible. And in the rock record, that typically expresses itself in the form of faults. So these are cracks in the earth along which there's been movement either side. And there are different styles of faulting depending on whether that rock has experienced tension, compression, or shear forces. So we have our normal faults formed under tension, our reverse faults formed under compression, and our strike slip faults formed under shearing. But today we're going to talk about styles of ductile deformation under those different tectonic regimes. And basically the three features that ductile deformation of earth materials can result in is folding. So folding results from compressive stress, so compressional stress, where literally layers of sediments have been folded and buckled. Tensional stress, actually, if we have ductile deformation, results in the thinning of the crust. So imagine a piece of clay or plasticine, and you pull it apart under tension, it's going to get thinner and thinner. The same thing happens to the crust when you put it under tension. And shearing stress results in this bending of the rock in different directions. So first of all, I'm going to talk about folds. So this is where sedimentary layers have been bent and buckled to form wavy features, literally folded features. They usually form under compression. So this is where we have some nice horizontal layers, which then experience compression, and they then get folded into these nice wavy structures. But they can also form in a few other ways. They can form by shearing. If you shear a rock and you form that nice bend, we call that shear fold. And also, if there's been vertical movement, so uplift and pushing up of the sedimentary layers due to something rising beneath it, you can cause folds. And you can also cause folds with the weight of something overlying, but they're less common. So here are just some nice examples. I showed you both of these folds in yesterday's lecture. You can see here, instead of being horizontal, our sedimentary layers have now been folded. And actually the sedimentary layers here are now vertical. Instead of being horizontal, they're now vertical. And this is a side of a much larger fold, So I'm not going to focus on of folds that are formed by shear too much, but this is how it works. We have a layer, this is our sedimentary layer, and then we have shear forces, so part of the crust is being pulled in a different direction from the other. You can see how you can form a nice bend in that sedimentary layer. So that's a shear fold. And we recognise it because of thinning in the bed on the actual fold itself. We're not going to focus on that today. But something I'll mention a little bit later is where we have folding formed by vertical movement in the crust. And a really nice example of this is where we have salt underground. If you remember when I talked about evaporites, you can have a layer of salt, so a layer of evaporite underground. Salt has a very low density. The different salt minerals have very low densities. So over a long period of time, that salt will try and rise up through the crust because it's less dense, and it forms what we call salt diapirs. So as that salt pushes its way up through the sedimentary layers, it can cause folding. So that's another way we cause folding. But I'll mainly focus on the folds that we talk about when we talk about compression later on. So just to introduce you to a few terms that we use when we describe folds. So where we have, if you like, a smile shape, we call that a syncline. So it's like the letter U or the letter B. And where we have an arch shape, it's like the letter A, that's how you can remember it. We call that an anticline. And we refer to the layers on either side of the fold limbs, just like your arms and legs, we call them limbs. And in a syncline, the limbs dip towards the centre of the fold. In an anticline, they dip away from the centre of the fold. And just to show you some photos, so this is a nice example of an anticline here, where our beds have been folded into this arch shape. And this is a nice example of a syncline, where they've been folded to this U shape. And you can remember it, S for smile, A for the shape of the fold. You can remember that anticline. And obviously they come in pairs in real life. When you fold a horizontal layer into buckles like that, you get a series of anticlines, synclines, anticlines, synclines, and they all share limbs. So here you've got your nice syncline, and this limb is obviously the same as the left-hand limb in the adjacent anticline. So just some more terms. So we talk about a plane that dissects the fold in two. This is where it meets this side. A plane that dissects the two limbs in half, we call that the axial plane. And where that axial plane meets the surface of a bed up here, we call that the fold axis. Okay? So the fold axis is a line, the axial plane is two-dimensional, it's a plane. And the beds dip away from that fold axis. That defines the fold axis. And we can also describe folds about whether they're symmetrical or not. So if you have a symmetrical fold, that means the angle of dip either side of the fold axis is equal on both sides. So if we measure dip from the horizontal, so if the bed is no longer horizontal, it's like that, we measure that angle, and that's our angle of dip. So in a symmetrical fold, the dip of the beds either side of the fold axis is equal, so it looks symmetrical. This is a nice example here. So our axial plane cuts all of the hinges. We call this part of the fold from the centre of the fold the hinge. It cuts, the axial plane cuts all of the hinges. We have a different limb either side, and as you can see here, the angle of dip on either side of that axial plane is roughly equal. So if we have increasing compressional stress, we tend to form asymmetrical folds. So you can see here, the dip from the horizontal of the bed on this side is almost 90 degrees, so maybe 80 degrees, which is greater than the dip on that side. As you can see, the dip from the horizontal is much less, maybe 60 degrees, something like that. We call that an asymmetrical fold. And eventually, under more compression, you can actually overturn your fold. So you go from a symmetrical fold to an asymmetrical fold to a fold which is completely overturned. And what happens in those folds is that on this limb, the beds are now upside down. So when we're looking at beds in our sedimentary sequence in the field, that's why it's important to look for clues to see if the beds are the right way up or upside down. So this is a nice example of an overturned fold here. And you can see it in the picture above. The beds on this side are actually upside down. And if that fold gets pushed over even more, so that the axial plane is actually more or less horizontal, we call that a recumbent fold. And this is produced under regimes of extreme compression. And this results in extreme shortening of the crust. You imagine if all these layers were laid out flat, that would have been the initial length of the crust. But through folding like this, we've shortened what might have been this length of crust into something that's only this long. Because compression always wants to shorten the crust, it wants to compress it. So when we talk about the fold axis, not all fold axes are horizontal. If that fold axis is horizontal, we call it a horizontal fold. But sometimes it actually dips itself. We call that a plunging fold. So you can see here the fold axis, this line that meets the bed. When the axial plane meets the bed, if that's dipping, we call that a plunging fold. These are just terms that I want you to use. And one thing I'm going to get you to do in the labs, not next week, there will be no labs next week, but the following week, is where we're going to start looking at geological maps. So a geological map is where we have a map, and it's colour-coded according to the rocks we see on the Earth's surface. And what it's really important as a geologist to do is to be able to interpret the patterns of those different colours, the rock types on the Earth's surface, in terms of the features below. And this just gives you a simple example of what an anticline might look like on a map. So as you can see here, this is a cross-section, so that's another phrase you should be familiar with. A cross-section, this is literally where, imagine the Earth has been sliced, and what you'd see if you were to look at that slice. This is our cross-section, and then this is what we'd see on the surface in terms of our geological map. If we saw an anticline, and obviously every Earth surface has been eroded flat, what we'd end up seeing is older rocks in the centre, and then repeated either side, gradually younger rocks. And if you were to measure the angle of dip, so the way the orientation or the dip of that bed from the horizontal on either side, you'd see that the beds were dipping away from each other from that centre. And that's what it might look like on a map. Whereas actually in a syncline, it's the other way around. You can imagine our nice syncline, our smile. If you were to roll that down and then look at a geological map, what you see is your younger beds in the middle, which get progressively older. Because these rocks are underneath these rocks, which are underneath these rocks. We'll do more of this in the lab, I just wanted to show you that there. Mainly because I wanted to show you what plunging folds might look like if you had them on a geological map. So a plunging fold is where your fold axis is dipping from the horizontal. And actually, if you were to erode that down and look at it, what it might look like on the surface, you see these pointy structures almost expressed on the surface. And it forms these really nice formations. And I think I showed you one here. This is a plunging anticline in Iran. Iran is a beautiful place to study geology. It's experienced large amounts of compression. So this is Iran in the Middle East. It used to be part of an ancient ocean, but because of a convergent plate boundary, it was now, the ocean was destroyed basically, and we have a lot of folding. And it's one of the reasons why Iran has so much oil, is because those folds can trap oil underneath an impermeable layer at the fold axis. But another reason it's good to study geology in Iran is because it's very dry. There aren't many soils and trees covering our geology, so we can just look at aerial photographs and figure what's going on. And this is a nice example of a plunging anticline. So this mountain ridge at the top has beds dipping away from it, from the central axial plane, and it's been eroded almost flat, and you can see where that fold dies out. because that fold axis is dipping in this direction. I'm actually in London, so I'm not from London, but I'm from the UK. It's only about 2 hours actually to London from where I live in Wales. So London is on a giant plunging syncline. Why am I telling you this? Because actually, it's really important for hydrogeology. So if we take a cross-section of London, so we slice the Earth's crust, and we look at what it might look like underground, see this green layer here, that's made of chalk. And this particular chalk is permeable, it allows water to flow through it. It's porous, it can contain water within its cracks and its pores. But the rocks either side of that chalk are not permeable. They don't let water travel through it. So what happens when it rains either side of London, that water will travel through the earth until it gets to the bottom of the fold, where it stops, and then it collects underground. So underneath London is a really nice, what we call aquifer. It's an underground reservoir of water, and that's where most of London in the UK gets its water from. So this is just a nice example about understanding what the geology is beneath your feet can actually help humanity in terms of resources, and water is obviously an incredibly important resource for all humans on that. All humans, yeah. So if you have folds produced by compressional tectonics, what tends to happen is you get these nice fold axes parallel, or 90 degrees rather, to the direction of the compression. And we get these really nice mountain belts and fold belts formed at 90 degrees to that pressure. Not parallel. So yeah, roughly parallel to that plate boundary. If you have two plates colliding, the mountain belts will be parallel to the plate boundary and about 90 degrees to the pressure direction. But we can actually produce some fold structures that instead of being elongated, they might die out, they might plunge in the end, but they're elongated structures. We get these circular structures, they're more symmetrical, so they dip away from a central point. And instead of being formed by compression, these tend to be formed by vertical movements in the Earth's crust, bend or warp our beds downwards, and we call these domes and basins. So basically, if we have something underground that's pushing our sedimentary layers up, then it forms this dome structure, which has a central point away from which all beds are dipping away from. The beds are dipping. And if you were to erode that down, then you can see the oldish rock exposed in the middle. And these are really, really important for industry. Quite a lot of oil reservoirs around the world are formed in these dome structures. Because what these domes nicely do is collect oil underneath them. If you have an impermeable layer that won't let oil through, and there's some oil traveling through the crust, it can collect under these dome structures. And the opposite can happen if you have something heavy, or you get thermal subsidence. So if a piece of crust falls down, it can contract, and the beds end up being walked down into what we call a basin. And in a basin, all the beds surrounding it dip towards the central point. And I just thought I'd show you this because it's really nice. I've talked about the salt diapirs and how they can form domes. So that's because salt rises up through the crust, it bends and warps our sedimentary layers above it. And this is a nice example in Iran as well, I believe. Oh no, this is in Canada, sorry, I thought this was the one in Iran. But see this central dome here? That's formed by the erosion of one of these salt diapirs that's actually now penetrated the surface. But all the beds around it dip away from that central dome. And this can also happen if we have rising magma, so molten rock underneath the ground. It's less dense than the surrounding crust, so it rises up, and that also can form these dome structures. And in rare occasions, if you have compression coming from lots of different directions over time, because your plate boundary is changing, you can also form a dome. That's less common. And this is an example of somewhere in the US where there's a dome structure. So all of these beds here dip away from that central point. So you can imagine it was like a dome before it got eroded. And that's because we had this large magma chamber, felsic magma, which eventually solidified to form granite. pushing up the sedimentary rocks underneath it. Okay, the wrong pictures have come up, so basically, ignore the pictures in this. But a basin is the opposite. That happens where either the crust sinks. So this can happen if it cools. Maybe you have a hot area of crust. If it cools, it can sink, forming this basin structure. Also, where the crust is being thinned, that can also cause the crust to sink. And also, sometimes around delta areas, so where a river meets the sea, there's so much sediment being pushed out of that river and deposited in a delta, it can actually cause the underlying beds to sink and warp and form these basins, which is happening outside the Mississippi Delta in the USA. So I'm now going to go through quickly different styles of deformation which are present in very different tectonic regimes. So we talk about a tectonic regime when we talk about different plate boundaries, basically. And there are three styles of tectonic regime: those relating to tension, those relating to compression, and those relating to shearing. And they all produce very different expressions of deformation on the Earth's crust. And I'm mainly going to focus on how the continents respond to this, because it's a bit more interesting. But obviously, ocean crust is involved in some plate boundaries as well. So where we have areas of the crust that are being pulled apart, remember I told you that near the surface we tend to have more brittle deformation, because we're under low confining pressure. As you get deeper into the crust, because we've got that higher confining pressure, remember those experiments from geologists, we tend to have more ductile deformation. So what happens near the surface is we get lots and lots of normal faults. So normal faults are the faults that are formed by tension. So you pull a rock apart, if it deforms by brittle deformation, one side, a crack will form, and one side of that crack will move upwards relative to the other. And in a normal fault, it's always, so the hanging wall side will always move down in relation to the footwall side. So remember your diagrams from the last lecture. And this happens on the surface of the crust. We get lots and lots of normal faults. And then as we go lower in the crust, we get ductile deformation. So in this case, we've got tension, so we get crustal thinning. So our crust becomes a lot thinner, because like our plasticine, like our clay, if you pull it, it will get thinner and thinner and thinner. And one feature of these places where we have a lot of extension, a lot of tension in the crust, is that we have normal faulting, but we produce these nice central rift valleys. So a rift valley is a dip in the Earth's crust, which either side has normal faults. It's bounded either side by steeply dipping normal faults. And that's what we tend to get where we get areas of the crust that are being pulled apart. And these normal faults tend to be quite steeply dipping towards the surface. As they get deeper in the crust, we get hotter, we get more confining pressure, they die out. They become more gently dipping, and they die out. And this produces some really spectacular landscapes around the world. This is just another diagram illustrating what I just talked about. So, for example, in Africa, we have this big hot spot, this mantle plume, rising up from the mantle. And it results in pulling apart extension and tension of the crust above it. And where we get that tension, the pulling apart of the crust, we get nice normal faults forming near the surface. And we get this nice central rift valley, as well as volcanoes forming as well. And these rift valleys collect a lot of sediments from the mountains and fault scarps either side of that valley. They're really important for collecting sediments. And I introduced the African Rift Valley actually when we were talking about plate tectonics. So this is Africa in the top left. We zoom in a little bit, we see three plate boundaries meeting at a central point. And each of those boundaries represents a divergent plate boundary. The crust either side is being pulled away from each other. And this part here at the bottom, this rift, is called the East African Rift Valley. And this is what it might look like in cross-section. So we have these very steeply dipping normal faults, either side of the central rift valley, which collects water and sediment. We have a lot of volcanoes, because the magma is rising up through cracks in the crust. Kilimanjaro is one of those volcanoes, and it produces some really, really spectacular scenery. So from yesterday, I told you that if you have faults that have moved relatively recently, they haven't stopped moving, they're still active. On the surface, you can actually see them sometimes as fault scarps. So where that block has moved up in relation to this block, we actually see it as a scarp on the Earth's crust. And actually this is the Rift Valley here, you can see either side it has these steep fault scarps which represent where the normal faults are. And this is Kilimanjaro, a really big and famous volcano mountain in Kenya/Tanzania. And as you can see here, just incredibly beautiful Rift Valley. Yeah, it just looks amazing. And the top left picture shows a shallower Rift Valley, less deep Rift Valley. This has a lot of magma reaching the surface at this point. And if we go to the one of the other rifts in this triple junction, so the East African Rift Valley is here, we have the Gulf of Aden here, and then the Red Sea here. This represents a slightly more mature Rift Valley formation, but again, we have steeply dipping normal faults either side of this central Rift Valley. We have fault scarps, but in this case, we've done so much spreading, we pull the plates so far apart, we're actually producing oceanic crust in the middle. We've got this ocean basin forming. And the opposite happens with compression. I told you that when you compress a piece of Earth's crust, what you're actually doing is shortening it. So when you're pulling apart parts of the Earth's crust, you're doing the opposite. So by producing these faults and by thinning that material, the crust is actually now longer than it was before. So you end up with a crust that's thick, you pull it, movement along that fault either side, those faults either side, and thinning of the Earth's crust results in crustal extension. And this diagram nicely illustrates it. It gets longer and longer and longer. And eventually, you keep pulling the crust apart around the Rift Valley, you might form an ocean. As I told you before, but forget that for now. Remember the faults, that's really important. So under compressional tectonics, I've given you two examples of features that form under compressional tectonics. So we have lots of folding. So wherever we have ductile deformation under compression, we produce our nice folds. Under extreme compression, we might form our nice overturned and recumbent folds. We also produce faults. So if you remember the type of fault that forms under compression, it's called a reverse fault. And that's where a crack forms under compression and your hanging wall moves over your footwall. So you end up with overlap and crustal shortening. And really spectacular features can occur in the continents. So where we have convergent plate boundaries, we have a lot of collision. We have a lot of compression, sorry. Where we have one plate that's much less dense than the other, the more dense plate will subduct under the less dense plate. Where we have two pieces of continental crust colliding, neither wants to sink back into the mantle. So we get a lot of folding and a lot of faulting. And the main type of fault that we see, particularly at continental plate boundaries, but at any plate, any compressional plate boundary, is called a thrust fault. And this is a reverse fault that's got a very low angle. So the fault plane actually doesn't dip very much. It's less than 45 degrees. So as you can see here, we've got one big fault, thrust fault at the bottom, and lots of smaller thrust faults. And what they do is they take up that stress, they take up that strain of the compression, and they result in crustal shortening. And the reason we get these very low angle thrust faults is because a low angle fault is more efficient at shortening the crust than a high angle. You get a lot more crustal shortening if you have a low angle reverse fault. So we get a lot of folding in the crust at these compressional boundaries and a lot of faulting. What we might end up with is what we call a fold thrust belt. So this is how thrust belts might form. So under any compression, we're going to get some folding. If any any ductile deformation occurs or gets unfolded. But at some point, that crust is going to fail. You can see at the bottom right-hand part of that diagram, we get failure of that fold axis. And this is a nice example of a fold which rests up where we've got loads and loads of folds, but actually the fold axis has failed. And we get a lot of these low-angle thrust faults where parts of the crust slide over the other parts of the crust, taking up a lot of that strain of compression. And this is an example in Nevada in the USA where rock B is actually older than rock D, and yet it's being thrust on top of it. So just to confuse geologists, this is what happens. So you get compression, you get a crack forming in the crust, and then as these rocks on the left-hand side move up along that crack, they can actually end up on top of it. So it just confuses the heck out of the geologist, because all of a sudden we get a sequence where we get a nice mudstone, sandstone, siltstone, and then we get the same rock again on top. And it confuses us. But usually we can recognize that fault plane and tell exactly what happened. And in terms of places where you get subduction, so one plate moving into the other, actually that plate boundary itself could be seen as just a very, very large thrust fault. So the hanging wall side is moving over the footwall side, except the footwall side is actually a plate in this case. So some people call these plate boundaries megathrusts. And obviously there's continuous movement along that plate boundary, so there's a lot of faulting. So faulting along that plate boundary, but also lots of other faults being produced inside. And if any of you remember the news in 2004 in December of that huge tsunami, which started in Sumatra, and then propagated a tsunami, the earthquake was around Sumatra, and then the tsunami propagated all the way around the Indian Ocean and caused hundreds of thousands of deaths. Well, it's believed that that was simply caused by movement along this megathrust, this plate boundary, because Sumatra lies on a convergent plate boundary where this plate here is moving under this plate here. And some sudden movement along that plate boundary generated this earthquake, which generated a tsunami and killed lots of people in the Indian Ocean. So that's what's thought to have happened. So finally, this is a little bit more, not more complicated, a bit rarer, I suppose. Where you have shearing tectonics, if you have ductile deformation, you produce these nice bends, S-shaped bends, or Z-shaped bends. If you have brittle deformation, where you have shearing tectonics, you form these really nice strike-slip faults. So the San Andreas fault in California, I keep using that as an example, is a really nice example of a strike-slip fault, where part of the Earth's crust is moving in a different direction to the part of the Earth's crust on the other side of that fault. And remember, there are two types of strike-slip fault. There are right lateral or dextral strike-slip faults, and there are sinistral or left lateral strike-slip faults. So imagine standing on one side of the fault. If the other side has moved to the right, compared to where you're standing, we call it a right lateral strike-slip fault. If the other side has moved to the left, we call it a left lateral strike-slip fault, etc. And in a simple case, we just have a nice fault with movement either side. We might have smaller faults forming either side. But actually what can happen is if we have a bend in that strike-slip fault, we can create local mountain ranges and we can create local basins. Because what happens is, imagine there's a bend and those rocks are moving this way either side. If they're moving in such a way that along that bend you get compression, you can start pushing up a little mountain range. If that makes sense. But if that bend occurs where the rocks either side are moving in such a way that you're pulling apart the rocks either side of that bend, then you get a basin forming. And that's called a pull-apart basin. And actually, where we were in San Beto, or where we didn't go in San Beto, where we could see from the highlands, that's exactly what happened there. It's called a strike-slip basin, and this is how it forms. So we have a bend. If we have a left-hand bend in a sinistral or left lateral strike-slip fault, you end up along that bend, pulling apart the rocks either side, and you get a nice little basin that collects sediment inside it. Whereas if you had a left-hand bend in a dextral strike slip fault, and the plate was moving this way, you get compression here, some reverse faults, some thrust faults, and maybe a small mountain range with some folds in it as well. And this is an example in California. This is our San Andreas fault. We've got lots of smaller bends. So the San Andreas fault is a right lateral strike slip fault. Where we have right-hand bends, we end up with extension and nice little basins forming. Whereas if we have left-hand bends, the two parts of the crust are actually colliding, so we get lots of reverse faults and folding in those areas as well. And this shows an aerial view of the San Andreas, which is just a large strike slip fault, essentially a transform fault. And all of these red areas are where we get these little pull-apart basins. So we have huge areas where lots of sediment is being collected in these nice little pull-apart basins. So that's all for today. What I'm going to move on to next time is I'm going to talk a little bit about these geological maps and how we can interpret them. But I'm also going to talk about geological time. And I know a lot of you have already done your lab exercise. It was quite simple this week, but we just looked at some outcrops on a sheet of paper and figured out what happened in what order. I'll be talking about that in a bit more detail. And I'll also introduce the different methods for dating rocks, like how I can tell you that the basalts we saw in the Mosey Creek are 40 million years old, how I can tell you that the sediments in the Tutu sandstone are only 5 million years old. I'll go through some of those dating techniques as well with you. So just to summarize today's lecture, so ductile deformation is where we get deformation that hasn't resulted in the fracturing of a rock, but we get a permanent change in shape or size. Folding is a really nice expression of ductile deformation, usually formed by compression, but not always. And we describe and classify folds according to their geometry, like whether they're symmetrical, asymmetrical, whether their fold axis is plunging, whether it's horizontal. We can also talk about gentle folds, which are quite open. We can talk about isoclinal folds that are incredibly tight. There are lots of numerous terms that you can use to describe these folds, and whether the type of fold produced will depend on the rock type, and also how much compression and the direction of compression that is experienced. And make sure you know what all those terms are. We can also form domes and basins where instead of compression we have vertical movement in the crust formed by rising material underneath the crust, or heavy material weighing it down, or crustal thinning. I've also given you a brief introduction about different tectonic regimes and how they generate different expressions on the Earth's surface. So it's really important you read this chapter in Understanding Earth to understand it further. We'll be looking at these structures a lot more in the labs in the weeks to come. As I said, there are no labs next week because all of the teaching assistants are away. And I'm away for 2 days as well. So yeah, happy reading.